Okay, so um, we're going to talk about the exam, right? So the exam is going to essentially cover, let me just put this on. The exam is going to cover two major chapters. If you don't remember what they are, I'll write them down for you. You're going to have chapter 3. And chapter 3 was basically the AC, let me write this better, magnetic field. We can call it creation due to three-phase AC current or power supply, either one what you want. So the idea is that we're going to have a rotating magnetic field, and you can tell the direction of rotation based on how the currents are, if it's positive sequence, negative sequence, also how it's connected in the machine. So essentially we had a machine here and we did a bunch of windings. And so this is a two-pole machine. Why is it two-pole? Because we only have 3 single phases that's on the stator. It doesn't matter if it's on the stator or the rotor. We talked about it being exactly the same. We simplified our work in chapter 3 that we just said the stator, they're on the stator because we don't want to worry about anything rotating, and this is going to cause a rotation of a magnetic field around the perimeter, and its rotation direction is going to be, is this A, B, C, or is this A, C, B, right? So it'll either rotate positive or negative depending on which your direction or what you consider positive, and it's going to just be specifically determined based on how you connect that. So all I know is that I have A, C, B here, right? And I can just move these around. So these windings that I see here, those are nothing more than just a set of windings. I actually don't have to call that A and B and C that's circled. I can connect those any way I want. So if you're an electrician in the field, you've got 3 leads coming out of a motor. You just connect them to whatever phases you want, and then you just check rotation. So you can swap these in any direction you want, and you're still going to get that magnetic field here that rotates along, and it's just gonna, its direction is gonna be based on doing your right hand rules and wrapping your fingers around the winding and then pointing your thumb. So what we did is we had some magnetic field. So let's just say that this is the A prime winding. So we're gonna say current goes into this, the X winding, and comes out here. So the corresponding magnetic field that we're gonna get is B sub A here. If we do the same thing for B sub B, if we have positive current going into B sub B, we're going to get something that is here. And then for B sub C, oops, this is B sub B. And then for B sub C, you're going to get something that is here, right? And then as you add those up vectorially, because you walk through the sine wave, and the only reason why these change is because I'm walking through, this is phase A, phase B is, phase shifted, and phase C is shifted as well. As we walk through those sine waves, if we start at time 0, we're going to get different values. And what that's going to do is it's going to impact the magnitude and the direction. So the direction of BA is only going to be in that direction shown or in the opposite direction if the current is going not in A prime, but if it goes in A. So the whole thing is to do these type of problems is to just draw your base values for where positive current is going to give me a magnetic field. And then I just plug in the values that I get here at one time. And then I just add those up vectorially. So literally I add my B sub A, which is going to be at an angle, plus B sub B, which is going to be an angle, plus B sub C is going to be an angle. I add those vectorially, and then I get a number. And then I rotate 30 degrees, 90 degrees, whatever you want. And then I'm going to go in time 2. I'm just going to continue to add those. But now I'm going to get a rotation in this corresponding addition, right? Because this is equal to B total. So as I walk through my sine wave, it's going to give me a rotation of b sub t, and it's going to be either in the forward or the reverse direction. So what I end up having is I have a rotation of my vector. This b total in a three-phase machine with proper phasing, 120 degrees, it's always going to be 1.5 times the maximum b that you're going to get per current going in each phase of the winding. Okay? And that's essentially how we're going to focus on doing chapter 3.
What would a question look like where we'd be able to apply this?
And the test or in the real world?
Real world or the test.
Well, which one? That's both. We can
Both.
Let's start off with the real world. So the real world one is you have an electrician that says, hey, I need to wire this motor up. What do I do? How do I wire it up? Because I can't decouple the whatever the device is connected to. The motor is connected to the whatever this external mechanical device is. I can't decouple it easily. Can you tell me how to wire this thing up? I see that this is 1, 2, 3, and I can see inside the machine. This is how it goes. You would have to tell them, okay, take phase A to this point, take B to this one, and C to this one, based on the fact that you can't decouple it. So a practical application is you cannot, just decouple it, and you can't just decouple it and test it. You actually have to get it right the first time. That's real world. For a test problem is, what would you do? Or a test problem is, what is the direction given ABC rotation or ACB rotation for a three-phase motor? It could even be a two-phase motor. So one of the things we haven't talked too much about is, what about single-phase motors? How do single-phase motors get rotation? You certainly need these magnetic fields to move along. Well, how do you get that? How does it operate? Well, all you need to do is do the exact same approach, and you might not get a constant amount of torque, but if you have a compressor in your refrigerator, or if you have, I don't know, a cheapy fan that's blowing air, you don't necessarily care about how long it lasts. You just got to get it to last a couple hundred hours. It doesn't need to have constant torque. As long as it's close enough, it's not going to vibrate too much, you can go with that. So essentially, you can use this and extend it to a single phase motor, and you can actually apply that to a case where you've got a single phase, and all you do is run a capacitor in the circuit so that you get a 90-degree phase shift between the phase that you have and the second phase. So by introducing that second phase, you get this rotating vector that goes around, and that's essentially how a single phase motor works. So the questions could be, what's the rotation, positive, negative, for a three-phase motor? Or if it's a single-phase motor, how does it, or a two-phase motor, what changes? What happens if I don't have all three phases? What if I've only got a plus and minus phase, right? A plus 120, minus 120. How do I get that to operate? And then go from there. And then what if I don't have mechanical spacing on the shaft of 120 degrees? What would I get? So that's one of the questions. The other question is, what is the speed of operation? So that's based on, this concept of how long does this magnetic field need to rotate along before, if I'm looking at A, how long does it take before I get back to a positive A? Well, we talked about a machine that has A and A here, A prime. What if I break that motor up in half? Well, now I erase this, and my motor now is broken up in half. So I have another A here. So my A prime winding, we'll call this 1 and 1. This is how I basically divided the motor up in half. So I've got two A terms. And so this motor electrically will only take 180 degrees of mechanical rotation to get 360 degrees of electrical rotation, because as this magnetic field is rotating, it's inducing current flow in that winding, or that it's inducing a current flow in the magnetic field. Well, that same current flow is going to happen 180 mechanical degrees apart. So that's how I get the 360 there. So that's pretty much where we would focus on the concepts or the discussion of what's important about chapter 3, which is, how do we get that nice rotating magnetic field, or how do we get a rotating magnetic field based on locating windings on a machine that has, relatively low conductance for magnetic energy. And then the next thing is, how do we get speed of operation? Those are the key parts for this chapter.
Wait, so Paul, did you just cut the motor in half because you only have one phase? Is that why you just did that?
Nope. No, I did not cut. I didn't do it in half. What essentially I did is I only showed 3 phases. I mean, I only showed one of the 3 phase. So the reason why I cut the motor in half is because, let me try a different color. This phase right here is the A prime phase. I've got this 1.5 B sub M that's rotating along. As it rotates, it comes into this positive point. Well, this is going to get me, if it's going to get me essentially a 0 crossing. I'm going to get a 0 crossing at that particular point, right? Because it's not cutting anything. If I rotate that all the way down here, I'm going to get another 0 crossing, and it's going to start increasing in the same direction as if it was here. So what I've done is electrically, this is going to be the start of my sine wave, right? I'm going to go up and down, and then starting back up at this point right here. This would be the A2 point. This is the A1 point. So what I'm saying is as I rotate along, I'm going to get 360 electrical degrees. And why is it 360? Because I've got a complete sine wave, electrical sine wave, 360 degrees for one sine wave, but I've only actually rotated it 180 mechanical degrees. So to produce 360 electrical degrees, I only have to rotate 180 mechanical degrees. So what I've done is by adding a number of pole pairs, right, or a number of poles, I've gone to a 2 to a 4 pole machine to get 360 electrical degrees. I only have to operate at half speed. So that means that I can run, instead of 3,600 RPM, I can run at 1,800 RPM. So that's how, in the real world, that's how we actually get motors to increase or decrease speed at a sort of a discrete time step. We enter it that way and we work it that way.
Okay, thank you.
Yep. Any other questions on that? Okay.
I'm sorry, I do have a quick question, Paul, that's kind of
Sure.
regarding this. I'm looking back through the slideshows. And so when you start talking about like the rotating magnetic field, you also show that the sum of the magnetic fields along with the angle sum, and then you do an example where you switch the rotation of them, and obviously they're still going to equal 1.5.
Yes.
But the angle changes. Is that something that you would want us to understand for the exam on Tuesday?
Yes. The reason why you need to be able to understand that is if you can't get those original angles to begin with, how are you going to know what the rotation is? So the 1.5 B sub M is constantly there. It's always going to be there. The question is, which direction does it rotate? Does it rotate in the counterclockwise or the clockwise direction? Well,
okay, and this is you made a MATLAB script that does something similar to this,
exactly.
right?
Yes.
Okay, perfect. Yep. I'm tracking. Thank you.
Yep, and you don't need to use the MATLAB script. That's just, you know, if people are familiar and comfortable with MATLAB, you can try that to see what you get. Other questions on chapter 3? Okay. Chapter 4, where we spent a lot of time, is basically synchronous machines. And really the focus is on synchronous generators, but there really isn't much of a difference between a synchronous generator or a synchronous motor. A synchronous machine always has to operate at sync speed. And sync speed is 3,600 RPM, 1,800 RPM, 900 RPM, et cetera, et cetera. This is for 60 Hertz. It's slightly different for 50 Hertz, but it's always going to operate at synchronous speed. It cannot operate at anything but synchronous speed. And the reason a synchronous machine does that, so it has, let's see, did I get that correctly? I've got, oops, draw this correctly, I apologize. So I've got one here and one here. So essentially what I have is I've got a stator winding, And this is what's interesting about synchronous or induction machine. The stator winding on a synchronous or induction machine is exactly the same. What's different is the rotor circuit on a synchronous machine is going to be, and I'm going to show this as a salient pole, it's always going to have a plus and a minus winding. So it's either going to be a permanent magnet or it's going to be a DC source. And the reason being is because that always gives me plus minus here, and I always have a magnetic field that operates here. If I want a constant torque output of the machine, or I want a constant electrical output of the machine, the rotating magnetic field that rotates because of the AC waveform that exists on the stator has to be distance-wise the same on the rotor circuit, on the stator circuit. So if these things, this angle here, this torque angle delta is not the same the entire time, then its output power is varying. And output power varying means vibration. It means wacky power numbers, where the power is increasing or decreasing, or the torque is increasing or decreasing. So a synchronous machine always has to run at synchronous speed. And as a matter of fact, if you try to start a synchronous machine across the line, which means you started at 60 hertz, it wants to instantaneously go to whatever the synchronous speed is, and usually you end up breaking shafts. It doesn't work so well. So that's why, like if we had an opportunity and I was trying to get us a tour of Maine Independence Station, they have these very large devices called load commutating inverters, which are basically a fancy way to say adjustable frequency drive, where their generators, their gas turbine generators cannot, you can't run natural gas and start them on because they have to be out of the flame path for a period of time before they back in, otherwise they'll melt. So they actually run their generators as motors to get the synchronous machine up to a certain speed before they turn the gas on. So that is a case where we have a synchronous motor, a generator normally, but it actually operates as a synchronous motor, and the machine doesn't care at all. But it has the DC field, it rotates at whatever the electrical frequency, synchronous speed, and the poles are, and you get operation. So then we did an equivalent circuit, and this is JXS, this is RA, and I get a terminal voltage shown there. This is that back EMF or that armature voltage, and what controls that is the amount of field current. And that field current is what is driving, if it's not the case of a permanent magnet, if it's the case of a traditional synchronous machine, you're externally controlling that field current by what's called an excitation system. And that excitation system is just always constantly adjusting it to meet certain control parameters. And, you know, we can discuss more of those control parameters at a later date and time. It's not relevant for this course. It's more important for later courses. But our field current is really just going to set EA. And then the amount of reactive power, Q, that's either in or out, depends on what the terminal voltage is, as well as the magnitude of that value of EA. So how do you increase or decrease reactive power, regardless of if it's a motor or a generator? You just adjust the excitation current. And that's why it's so important to have field versus EA. If you recall from the generator that we did more towards the beginning of the semester, and when we had an additional example, what we saw is that that value of EA was provided for all kinds of characteristics. So we actually had the load curve and the no load curve that was provided for that particular machine. And that is a pump storage facility. So in the daytime, it used to be in the daytime that it would operate as a generator, and at night it would pump up to the top of the mountain, so it would act as a motor. Anybody has a guess as to why that might be changing? That's why it would be pumping during the day and dumping power at night.
Solar?
Yeah, exactly. There's so much solar going on in the East Coast. Massachusetts, I think, has over a gigawatt of solar. What happens at night to the sun? It
Goes to sleep.
Yeah, it takes a nap, right? Exactly. So because it's no longer available, that 1,000 megawatts of power is completely gone. So all these old fossil-fired plants aren't necessarily running, because during the day you essentially have energy that is almost free because it's from the sun. Now there are some costs associated with the installation, but it's very cheap to do that. So at night there's no sun, and these fossil plants aren't running anymore. So your pump storage facilities are now running at night. as opposed to during the daytime. And that was exactly the opposite, because back in the day, the plant that I'm the most familiar with is Northfield Mountain, which I think is the second largest generating station in New England. There's 1,200 megawatts capability there. They were built in the 60s because there was some nuclear plants that were coming online, and nuclear plants run really well baseload. They don't like to go up or down. They like to stay at nearly 100% output. Well, that's great during the day because you've got lots of load, but what happens at night when there's very little load? The nuclear plants would have to back down. So instead of doing that, what they did is they said, well, let's run this pump storage facility and run it at night so that it absorbs the excess energy that the nuclear power plants are capable of doing. And then during the day, we don't have to have as much generation capacity, as many nuclear plants running to pick up the load during the day. That can be set up for us that way. And so that plant's been running for 50 plus years, and it's probably more important today than it was back then. So kind of an interesting thing. So that's kind of why that goes. But we had curves. Whoops, sorry about that. We had curves that do this, this, and this. And just by looking at those curves, you should be able to figure out what is what. This is the air gap line. Why is it the air gap line? Because it's going to be above the saturation characteristics of the line. This is the open circuit test, or the open circuit curve, no load, and this is the load line. This one would be plotted IA, right? That's the only curve that should be plotted with a function of current. And with that, we were able to calculate XS, the saturated reactance, the synchronous reactance, both unsaturated as well as saturated. And I don't know if anybody went back and looked, but if your own edification, if you wanted to look, you can actually see where our saturated reactances, there was a direct and a quadrature axis impedance that was provided in those data sheets. Those data sheets, the values that we got were pretty close to what they had calculated. And then that gives us our X of S. This RA, the only way we get that is from a DC test. But most of the time we can ignore that because X over R ratios for generators tend to be greater than 30. Very, very high. If it's a small generator, it's different. But X over R ratios of generators are very, very high, which means fault capability at a generator is very challenging because there's so much DC offset that's available to us. And we'll talk more about that next year if you take some follow-on classes, but essentially that's the primary difference. So that kind of was the synchronous machine. Once we had all those, all that discussion of the equivalent circuit model, then we could do some phasor diagrams, right? So we had a VT, we had an IA, and we had an EA. So just with this phasor diagram, you should be able to tell me if it's a motor or generator, and if it is exporting or importing Q. Anybody want to guess as to which is which? Nobody wants to guess. You don't have to. By the way, is everybody impressed with my wonderful office setup? I can show you where I'm located if you're interested. I'm in my basement.
Pretty good.
Rough. Anybody else is as sad as mine is?
It's so stylish, Paul.
My basement office?
Yes.
The challenge I have is that I have a fairly small house with 4 people, and it's just challenging to find spots where people don't want to interact with you too much, where you can get work done. So I set up a table, and I'm very proud of this, but don't laugh too much. This is my light that I installed, running an extension cord with an actual light fixture that I had set up. So I'm reduced, reusing, and recycling. So please don't laugh at me too much. But,
Nice.
anybody else want to share their awful setup? Or
One of my professors yesterday locked himself out of his house, so he was zooming in from his phone on his in his car.
oh boy,
Yeah,
wow, that's
pretty
creative.
impressive.
Yeah.
Yeah.
I won't do that. I'll at least try to do it a little bit more professionally, just in my basement. So I at least put up a screen. So, but Tony has a nice setup. He looks like he's a gamer. Tony's got a serious gaming
Geez,
setup.
Paul. Wow.
He's got a nice mic and everything. That's
Yeah.
Look at Liam.
This is just the office that's in our house already that I just kind of have taken over.
The office. You look like you're in an arboretum of some sort.
It's because the way the house is built, it's built on a hill, and they couldn't build anything here, so they just put a pond in the house.
Wow.
Yeah.
Can I move in?
It's, well, suffice to say, we have to cover all those windows there, or it gets very cold. So it's okay. I mean, it's not bad.
Sounds a lot better than just okay to have a pond in your house.
I want a house pond.
Yeah, no,
It's
I'm like
interesting.
chilling on
It's
the
very
couch.
Hopefully your parents aren't home.
No, it's just me. But
Oh, you're in your apartment. Okay.
yeah,
I'm sorry. I wasn't sure if people were actually staying home or what, though.
no, it's just me and my dog.
Liam, do you have any fish in your pond?
It's a better setup.
We had a frog that died 10 years ago.
And it's
Is
still
it
in
still
there?
there?
And then, what?
It's still in there?
No, we don't know what
Okay.
happened to it. We don't know it all existed. We have some plants, but they're kind of dying. And I have to clean the pond because it's disgusting. So I have to go get the pressure washer eventually to clean it out. But other than that, it's not bad. I mean, it's interesting. It keeps it nice and cool in the summertime, but it gets freezing down here in the wintertime because there's not a lot of heat down here because of
Yeah, I
that
can imagine.
massive thing.
Okay, so what
Yeah.
was the original question, Paul?
Yeah,
So the
what
original
was that
question
original
is-
question, Paul?
Original question is this a motor or generator? And is it an exporter or importer of Q? So there's two questions actually, Riley.
Is it a motor?
Or generator. I can just give you this phasor diagram on the test, and you should be able to tell me what it is just by looking at the phasor diagram.
Is it a motor?
Are you asking me or are you telling me?
I think it's a motor.
Okay, why?
Well, I'm comparing it to like a capacitor and stuff and how that usually looks, and that's like with the downwards angle, versus like an inductor, which would be like a generator.
No?
I don't know.
A
I don't think-
capacitor. So what makes a motor or a generator? A motor is only a device that imports power, real power. Okay. So what defines a motor is something that imports power. Something that exports power. This is real power. Is a generator. Importing or exporting reactive power doesn't even tell you if it's if motor or generator. That just tells you it's leading or lagging. That's all it does. It doesn't tell you any more. So to tell if this is a motor or generator, you can't look at it from the perspective of a capacitor or inductor because those are loads, right? We always would expect that power would go in, even though in an ideal world, it'll take power in. So you can't look at that from the perspective of capacitor or inductor. We have to look at it from some other perspective. And what's the other perspective? Well, if we were to go ahead and look at it this way, right? And this is just some JX. I just picked VT to be at an angle of 0. So my VT is here, right? And let's say that I've got an IA that's here. Let's say it's a lagging power factor, okay? The JXS that I would have gives me the 90-degree phase shift, right? Because this is actually what XS times I would be equal to. Then I just rotated 90 degrees because of the J term. Because of that, I have a positive delta, which means that if delta is positive, at least in this case with a lagging power factor, does everybody see why that's a lagging power factor? Current lags the voltage. Remember, we're using this as our reference point, so it's lagging at the output of the terminals. So we have a lagging power factor And that's how we're going to understand that this is lagging, but we see that delta is positive. Let's go with the condition where we have a leading power factor. So that is my VT. This is my IA. Would you all agree that this is a leading power factor?
Yes.
Okay. So I've got IA times JXS, rotate it 90 degrees. I get something here. This is EA. What can you say about delta? Delta is positive, isn't it?
Yes.
So delta is positive when current is out of the machine. Way at the beginning of the semester, what did we say about current going out of the machine? What really dictates whether that is going in or out of a box? What really dictates the direction of I?
Whether it's a motor or generator?
Whether it's a load or a source, right?
Source.
Load, it's generic, right, to say anything. So the direction of P will follow, and the current direction follows that way. So since IA is in the out direction, that's P. So whether it's leading or lagging power factor, our delta was always positive. So it's a motor. Why? Because our delta is negative. And let's take a look at that. Here's VT. That's always our phasor diagram. If I subtract my JIXS, let's draw the lagging power factor. So normally I would get a phase shifted one up here, but I'm subtracting it, aren't I? So subtracting it means it's actually down here. This is minus JXSIA. So my corresponding EA is here. What can we say about delta?
It's negative.
Negative. Is delta negative here?
Yes.
Delta's negative, motor. Positive, generator. Now, if I look back at my first two figures, so let me highlight these. My first two figures, those also tell you something about the reactive power. Any guesses? Make sure this is recording. Yes, it's recording. Look at the magnitude of EA here. And then the magnitude of EA here. The magnitude of EA is greater than VT here. How about in this case, the magnitude of EA is less than VT here. So I can tell if it's exporting or importing Q just based on the magnitude. If the magnitude of EA is greater than the magnitude of VT, it exports power. If the magnitude of EA is less than the magnitude of VT, it is importing power. And you'll notice here, is this magnitude less than VT?
Maybe a little bit.
Think so, right? If we draw this way, we have a little bit. Well, remember, in the case of a lagging power factor, here's voltage, here's current. My power triangle gives me a P and a Q that's both positive. So if it's a lagging power factor, whatever direction P is in, whether it's in or out, right? Q is in the same direction, right? So P is in a motor, it's out in a generator, so Q is out, right? If it's a lagging power factor. So what this tells me is because Q is going in, that means the motor is underexcited. And didn't I say if EA magnitude is greater than VT, it's exporting Q, whereas if it's less, it's importing Q? Isn't that exactly the same concept we have here? And it has nothing to do with the fact that it's a motor or a generator. It just has to do with the magnitude of EA and VT. So that's how you can tell, just looking at the phasor diagram. I can essentially just say, what is EA and VT? Does that throw you off? What is that? Is that a motor or a generator? you're shy, you can do a chat and do it that way.
It's a motor.
It's a motor. Anybody else agree? Anybody disagree?
It's a generator, isn't it?
Disagree.
I actually think it's a generator.
Yeah.
Okay, we have
Oh
one.
boy.
Pardon? I didn't hear that. I'm sorry. I didn't hear who spoke.
No, I
I
said,
said generator.
oh,
Oh.
boy. I think it's a generator.
We got 2 generators, and I thought I had 1 motor. Why do you say it's a generator?
Never mind. I was looking at it backwards. My bad.
Okay,
If
so
you use
why?
the VT as 0, then the EA is a positive angle
Yeah.
from it.
It doesn't matter whether it's 0 degrees or minus 20 degrees or whatever. As long as the angle of EA is greater than the angle of VT, you're going to have a generator. So this looks like a trick, right? But is it really? Isn't delta positive? And that's what I said
Yes.
here. Is it positive or negative? I never once said, is it greater than or less than 0? I just said, is it positive relative to VT? So if
Yeah.
if you don't like that, you can just say angle EA greater than angle VT. Oops, this is less because that's the motor one, sorry. Then it's a motor. If it's a generator, then the angle of EA is greater than the angle of VT, then that makes it a generator. So we've determined that's a generator. Is it leading? I mean, is it importing or exporting reactive power?
Should be exporting, correct?
Why?
Because EA is larger than VT.
Magnitude of EA is larger than the magnitude of VT. So it's exporting power. Okay. And I think the last thing that we talked about, we did all the testing, right? We did the saturated, unsaturated. We should be able to go back and forth and be able to calculate impedances, whether it's saturated or non-saturated. How can you tell if you're saturated or non-saturated? Well, remember, here's our open circuit characteristic. Here's our air gap. Whoops. Try to stay a little more in line with it. So this is the air gap line. I mean the saturated characteristic, open circuit. And the air gap line basically just does this. So you can tell where you are. So if I give you a field current, but I don't actually give you a curve, you should be able to say, I'm saturated or not, because the slope, if I draw a slope of this line, right, this air gap line, any voltage that I have here, so let's just say this gives me a field current of 5 amps, I can tell you that that's saturated because the air gap voltage is greater than the voltage that's on the open circuit characteristic. When the air gap voltage equals the open circuit characteristic, you're in the unsaturated region. So you should be able to tell just by looking at it, is it unsaturated?
Can you write that down, what you just said?
Uh,
Or go a little slower on what you, so if the air gap voltage is bigger than the open circuit voltage, then it's unsaturated, and vice versa, like if they're equal to each other.
I think I said it differently than that. So remember, we have 3 curves. We have the open circuit characteristic. We have, and let me draw a separate color. We have the air gap line. And the air gap line is always going to be sort of linear. And then we have the load characteristic. And that's where we're plotting IA. In all cases, this is IF. So you can tell when you're saturated, right? And you know you're saturated is this point right here. You can see that it's starting to curve away from a straight line. So if the magnetic material is unsaturated, it's going to stay linear. It only starts to become nonlinear when it saturates. And you can tell saturation because the air gap line, the air gap line is linear the entire way. The open circuit characteristic is nonlinear, it saturates. So if you've got a reading of a voltage here at, let's say this is 5 amps, and your voltage, if I tell you your voltage is, let's say it's 200 volts on the air gap, and then I tell you the voltage on the open circuit characteristic is 170, you know you're saturated because these two are not the same. If I said, okay, my field current is 3 amps, and I've got an air gap voltage of 130, which is also equal to my open circuit voltage, because those are the same, right? They are linear. There's no difference between the two. So this would mean that your 3 amps is in the unsaturated region of the load characteristics, and your 5 amp is in the saturated region. So you can tell just by looking at the air gap line or looking at the data for the air gap, if the air gap voltage or current is different. So another thing is if I said, okay, to get 480 volts, let's say I said to get 480 volts here, on the air gap line, let's say it takes 15 amps. To get to 480 volts here, let's say it takes 20 amps. Then you know to get to 480, you have to operate saturated because your air gap line is not physically realizable, but the open circuit characteristic, you have to drive it at a higher field current to get there. So you can even look at it from a perspective of field current to see if you can get the same voltage. So it's either way, it's the same thing. Does that clarify?
Yeah, it does. Thank you, Paul.
Sure. So the last thing I think we talked about, remember if it's a motor or a generator, right? We have the efficiency calculation, which is always P out over P in. If it's a generator, P out is electrical, P in is mechanical. If it's a motor, it's the exact opposite. It's still P out over P in, but it's mechanical over electrical. And I think that's it. Questions for me?
This test is going to be on Tuesday, and you said it's going to be like 3.5 hours or something?
Yes. Did you take a look at Blackboard? There should be an announcement already.
I did not take a look at that. I'll take a look at that in a second.
Yep. I believe if anybody can comment or confirm, I already posted an announcement on Blackboard giving you the specifics of that.
Yep, you did.
Okay. And I think I gave you all the details, so that way people who aren't attending the live sections are staying current with Blackboard. And you can go from there. What else? Okay, well, if there's nothing else, I'll sign off. I will encourage you, if you're interested in the utility industry or the power industry, there's an EET 460 class that's a general education elective. It also counts for population environment. So it's an EET tech elective. I don't know for ECE. I know there's a couple ECE students taking the class, or a few. If you're interested, that does, I believe, count towards the concentration in power systems. If you want to talk more about that, either if you're ECE or EET, that's one of the classes you may want to consider taking. You should do pretty well in it because you've got a lot of the background that we've already discussed. We'll just get into more discussion of renewable generation, but everything is basically related to the grid. And I've done probably 50 projects, and of any size, they're going to have to interconnect to the grid. If it's something that you're going to run your camp off of, you don't have to analyze it, but it works a little bit different there. So with that, if I can take over control again. I have to stop sharing that. Sorry, it's very quirky, and I apologize for doing that, but just very quirky. So questions for me?
Paul, I wanted to ask a question about the thermal class. You said I should take the MEE course, MEE 230. Is that correct?
Well, let's talk about that offline. So just send me an email and I'll give you a response to that. I talked about that briefly at the beginning of class, but let's talk about it not right now, just because I don't want to mix the two up. So
Okay, all right, that's okay. Thank you.
Perfect. All right. Well, if there's no other comments, have a wonderful day and weekend, and I will look forward to talking to you soon. Thank you very much.
Thank you.
Bye-bye.
Thank you, Paul.